welcome back to physics labs in the time of the coronavirus scare. Today's lab, what we're going to do is a take-home lab. So I'm not going to this time video myself doing all the data for you and having you write it down. Instead, I'm putting this video together to show you what you can do for this lab. It's going to be a simple geometric optics lab, and it is a do-at-home type lab. I have all the materials on the table behind me. I bought all of them today from Walmart for about $10. So you can get all the materials if you have none of them already lying around at home. You should be able to get them fairly inexpensive, either from Walmart or Amazon or wherever you want to buy this stuff from. So let's have a look at the material before I show you the setup. Alright, so this is basically all the materials that you will need for this lab. You may optionally need one more thing for it, which I'll get into in a moment. Basically, you'll need a magnifying glass of some sort. This was probably the most expensive thing of this list of stuff. I had to pay a good $5 for it, so not terribly expensive. It's just a simple magnifier. You can look at stuff under the magnifying glass, so you get bigger and smaller, mostly bigger. Okay. I have a thing of Play-Doh. This right here, we'll see what this is used for in a minute. The Play-Doh is going to be used to hold the magnifying glass for me. And then besides that, you could use modeling clay, or you could use sand, or if you have a container that just fits the magnifying glass so that it's stood up or stood on its side, one or the other. Any of that's fine. By the way, I should say about this magnifying glass, you want this kind that's smooth, not the kind that's sort of ridged. The other kind is what's sometimes called a Fresnel lens. It might work, but I think the magnifying glass will work better for what I'm trying to do here. Next item that you need is a candle. I just got some simple votive candles for, I think they cost like $1 or something, nice and cheap. And really you need one of them, just one. Now for the candle, I would recommend one that's freestanding like this, not the type that's in a glass, because what we really care about on the candle is the flame. You can use one that's in like a holder as long as the flame sticks up out of the holder. Okay, next thing that we need is something to light the candle with. You can cheat and use a lighter, which I'm going to do anyway, but if you have matches, or if you want to go outside and it's a sunny day and light it using sunshine and the magnifying glass, go for it. Practice safety as always. And then the last item that we'll need, the last two items, you'll need one meter stick, and you'll need something to project the image onto, a piece of paper for example. So here's one piece of paper. It doesn't necessarily have to be blank. You just need something that the image can be projected. Alright, the meter stick, by the way, is not entirely necessary as a meter stick. You could get a measuring tape or a ruler or whatever. You just need to be able to measure distance. And so I have one of those here, but you can use something else if you'd like. Alright, so let's talk setup now. You need the magnifying glass to be held upright. And So to do that, you can stick it into the Play-Doh. You can even stick it into the Play-Doh container, or if you have a glass of sand or something, that works. And you need to be able to measure where the lens is located. So you're lining up maybe the base of this thing, because it's right under the base of the handle, is right under the lens. You're lining that up as the position of the lens. The second thing you need to do is to put the candle somewhere, and it should be centered on the lens. So you will need something to hold the candle up high enough that it's centered on the lens. You can use a stack of books, for example. Alright, so once you've placed the candle in line with the magnifying glass, you can go ahead and light it. And actually, you're going to want to position it some distance away from the magnifying glass while lit. It's a bit of an aggressive flame. Alright, so now we have one lit candle, and we want it roughly centered on the magnifying glass. So let's raise it up to where it's centered, like that. Now for the next step, what you're going to want to do is turn off the lights. Get a nice dim room. So we have a lit candle. We have a lit candle and we have a magnifying glass. We hold our paper somewhere on the other side of the magnifying glass. And we want to move the paper until we have a nice sharp image of the flame on the paper. So let's lower it a little bit. And there's actually two focal lengths for the magnifying glass, by the way, because there's a little inner one and then an outer one. They may focus in different locations. But we can see right about here, there's a nice sharp image of the flame itself, the candle. Okay, so if I move it closer, it gets blurry. If I move it farther away, it gets blurry. So right about here is where it's sharpest. You can actually see it, although I don't know if the camera picks it up very well, with the lights on, for what it's worth. Right here, but it may be a little harder to find where it's sharpest. For what it's worth, I need to write down some numbers now. This is at the 23 centimeter mark. The magnifying glass is at the 40 centimeter mark. Candle is at the 51 centimeter mark. So let's write those three numbers down. So we have image or paper. At 23 centimeters. Magnifier at 40 centimeters. And candle at 51 centimeters. We need to change this into a new coordinate system where the magnifying glass is at the origin of our coordinate system. So I'm going to draw a little diagram here. Here's my magnifying glass. This will be sort of at the origin, and everything else we want to measure with respect to that. Okay, so right here is where my actual candle is. And then somewhere over here is where the image of the candle. And you'll notice, by the way, that the image is upside down relative. We need to label these distances in terms of the image, so we will call that DI, and the object, the actual candle from which the image was made, which we will label as DO. Now the relationship should hold that 1 over over dO equals 1 over f for the magnifier. Okay? So what we're going to do is we're going to record these values from this table. So this is at 40. The distance from here to here is 17 centimeters. So DI is 17 centimeters. 40 to 51, DO is 11 centimeters. And by the way, the sign convention, if the image is formed on the opposite side of the magnifying glass from the object, then both have positive values. If they're formed on the same side, then DI has a negative value. Alright, to get the two heights, what we do is we just measure them. So we take our ruler, we measure the height of the candle here, preferably without setting the ruler on fire. It's about 2 centimeters for our object height. Now we look for the image. On this paper again, we find the image here and we measure the image height, which appears to be about 3 centimeters. Alright, so we just measured that the image height was 3 centimeters. We just did it. The object height was 2 centimeters. This right here, this height should not change when we move the candle, but this right here will change, as will this number and this number, as we move the candle. So what you're ultimately going to do is construct a data table over here. The data table should have on it the following information. First of all, record the height of the object above the data table. You may check it periodically if this takes you a while, because if the candle does die down, then maybe the flame will die down some too, but it should basically be 2 centimeters. Now you have to put the following information. The object distance, so this and this are basically the two independent variables, although this one is not so much a variable. You need the image distance. You need the ratio, DI over DO, of these two. You need the image height, and worth noting, it's upside down, so this is technically a negative number. So you have the image height. Since it's a negative number, I'm going to put a minus sign up here so we can just record positive values everywhere. We have the magnification. Magnification is the ratio of HI over HO. Again, I'm going to put a minus sign here because all of these will be negative, since all of these were negative and this was positive. And in the last column, percent error. Okay, to fill out these columns, we need to know something about the theory. So let's put the first round of data in here. This right here, DO, we found was 11 centimeters. DI was 17 centimeters. DI over DO would be 17 divided by 11. Height of the image is 3.0. The magnification is 3.0 divided by 2.0, so that's 1.5. And now for the percent error, what we have is we're comparing this and this. So M, the magnification, H, image, height of image over height of object should also be negative of distance of the image over the distance of the object. Okay, so we're really comparing these two quantities. So let's pull out a calculator. I have my phone on me, so that's what my calculator is going to have to be. Alright, first of all, let's get this as a decimal. 17 divided by 11. It says it's 1.5454 repeating. At two significant figures, we might just say it's 1.5. But for the sake of doing a non-zero percent error calculation, let's call it 1.54. So our percent error then is going to be the difference between our, oops, I erased the wrong thing here. It's going to be the difference between our theory value and our experiment value divided by the theory value. So percent error, in this case, is the absolute value 1.54 minus 1.5, all divided by 1.54 times 100%. Multiplied by 100%, this is 2.9% error. Okay. Now, once you've filled out this table with some more values of DO, DI, and etc., the last step that you should be taking is to make a graph. And that graph should have on it DI versus DO. And in fact, you're going to want to linearize it. So perhaps you should graph 1 over DI versus 1 over DO. Alright, so DI versus DO. Both are actually positive. And you'll get some graph, and then you want to linearize it. And if you have 1 over DI, have 1 over DO here, then you should get a straight line whose intercept ends up being over the focus. So we want to measure the focal length, in other words, of this lens. We're making use of the fact that 1 over DI plus 1 over DO is 1 over F. That's the thin lens equation. And so 1 over dy, this would be sort of like your y, is negative 1 over do. This is your x plus 1 over F. So this would be your b. Slope, for what it's worth, should be minus 1. Okay, so now you have one further thing to compare experiment to theory to. Is the slope actually minus 1 when you do this? And for that matter, did you get a line? You should, once you do it like this. But is your 1 over, excuse me, is the slope actually minus 1 as it should be? Alright, so what you actually have to do for this lab, set up the experiment, measure at several values of DO. Where does DI form? What's the ratio? How tall is the image? What's the magnification? What's the percent error? And then make a plot 1 over di versus 1 over do, and from that plot, determine the focal length of your lens, and determine whether or not your slope is -1, and if not, how close, what's the percent error, and so on. All right, so that is your take-home lab for this week. Good luck.